Thank you very much for the opportunity to speak in this seminar. For me, as I was telling you before, it's really nice because, especially in my research, it's really common to look for materials, articles, and so in this seminar, since all the talks are recorded, I could find a lot of talks. I think that more than 10, especially related to my research. And for me, it's really special that, okay, now I am giving a talk about my research in the place that I usually look for nice talks. So I will talk about the work during my PhD and the work that I'm trying to continue in this postdoc. So first, I will give you just some words about the Cremona groups and the Sarkisov program. In all my work, I work at overseas, and so I will denote the M as the projective space over the field C of complex numbers. And the Cremona group is the group of birational self-maps of the M. And the study of this group has been a very active area in algebraic geometry. And for example, for n equal to 1 and n equal to 2, we have really nice descriptions for this group in terms of generators. And for example, for n equal to 2, we have the famous Nader-Castelnuovo theorem, which says to us that the Cremona group of the projective plane is generated by the automorphisms of P2 together with the standard quadratic transformation. But for higher and for bigger n, we don't have a reasonable description in terms that, okay, we can give a description of this group in terms of a nice set of generators. But by using tools from the minimal model program, which I will abbreviate by MNP, Blanc, Lamy, and Zimmermann were able to show that certain good candidates to be the generating sets of this group in higher rank cannot play this role. And so this minimal model problem, which we will explain better soon, gives us a really powerful machinery to deal with the study of this group. And under this point of view, Pm with the morphism from Pm to spec of C is a more fibered space. Soon I will explain what this concept is. And now I will give you just a rough sketch of the MNP. Essentially, the idea of the MNP is giving a projective variety with mild singularities at least manageable in this context. The idea is trying to find a distinguished representative of the birational equivalence class of this variety, which is simpler according to some senses. And so, by mild singularities, here I will mean X singularities which are terminal. So here I start with X a terminal projective variety. And so, depending on the geometry of the variety, when I run this MNP, basically my outputs will be of the following types. So I can obtain a variety X prime with canonical class map. And so in this case, we call this X prime a minimal model. And this happens with the Kodaira dimension of the of our initial variety is greater than or equal to 0. And or we can end with a more fiber space. And so this happens with the Kodaira dimension of our initial variety is minus infinity. And so this Kodaira dimension is extremely related to the geometry of our variety. So basically we have these two different outputs. And it's important to note that the NNP completely holds for dimension less than or equal to 3, and the MNP is conjectural in some cases for higher dimension. So this program is not complete yet. And just to let you know the importance of the NNP, Kushevika got the Fields Medal for his contributions to this program in higher dimension. And now we saw that we have two different outputs of the NNP, variety X prime with canonical class F or a modern fiber space. And now I will define what a modern fiber space is. So a modern fiber space is a normal, a projective variety X with a morphism F from X to a lower, where S is a lower dimensional variety. Such that satisfies these following properties. The push forward of the structure shift of X is the structure shift of S. And so this condition by the Zariski main theorem implies that the fibers of this morphism are connected. To the anticanonical class of X is F ample. So this condition is expressed by saying that the anticanonical class restricted to the fibers of this morphism are ample. So in this case, this implies that all the anticanonical classes of the fibers are ample. So this implies that the fibers are Fano varieties. And the third condition is that the relative picker rank, which is given by the difference of the picker ranks between X and S, is equal to 1. So all of this define a more fiber space, and we denote such a structure by X bar S. Okay. Now we have this definition of more fiber space, and we saw that they are possible outputs of the NNP. But the point is that the way that I perform this NNP is not unique in the sense that I need to make certain decisions along the process. And so, depending on the way that I run this program, I can obtain two different outputs. In this case, for example, if I start in this case with a variety with quadratic dimension minus infinity, I can obtain two different outputs, but these two different outputs are naturally connected by a birational transformation. And we have this result called Sarkisov Program, which will say to us that how these outputs, in this case of more fiber spaces, are related. So the Sarkisov Program was a result proved by Corti in 1999 in dimension 3, and Hakon, McKernan, and higher dimension, and in 2013, and which says to us that any birational map between more fiber spaces is a composition of simpler birational maps called Sarkisov links. So here, if I have a more fiber space x0, x0, and a birational map to a more fiber space xn to Sn, we can decompose this map as a composition of finitely many Sarkisov links, which will be birational maps, simpler, in the sense that they have explicit description, general descriptions in some cases. Here I have 1, 2, and for example, for dimension 2 in this case, where the more fiber spaces are rational, we can show that in this case, the rational more fiber spaces are given by P2 and the Hirzebruch surfaces, and all these links here appearing are basically point blowups of P2, the involution of F0, which is isomorphic to P1 cross P1, which will switch the two factors, and elementary transformations between Hirzebruch surfaces. And now this is a general introduction, so now I will tell you a little about log Calabi-Yau geometry. So probably you must have ever heard about Calabi-Yau varieties. And now I will define what Calabi-Yau pairs is, and they can think of generalizations of Calabi-Yau varieties. So a Calabi-Yau pair is the data. Okay, I consider a log canonical pair XD is a Calabi-Yau pair with the log canonical divisor, which is the canonical class of the ambient variety plus this divisor here, is Z linearly equivalent to 0. So this Z is just to mean that I am assuming here the standard linearly equivalence. Of course, there are some definitions of Calabi-Yau pair which I can replace Z even by Q and R, but for my work, I worked under these assumptions. And so if I consider, in this case, N as the dimension of our ambient variety, so this will imply that exists a top degree rational form, unique up to non-zero scaling, such that the divisor of this form plus d is equal to 0. And we call, by the use of language, this rational form the volume form associated to the Calabi-Yau pair. And just to give you some base, the simplest example, if you consider our ambient variety to be P2, so basically we have 4 possibilities for this boundary divisor. So since the Picard group of X is generated by a line, and the canonical class of P2 in -3 times a line. So basically we have these 3 possible configurations for D. In this case, D can be the sum of 3 concurrent lines. D can be the sum of a conic in a line. Conic and line. D can also be a non-singular cubic. And also, D can be a nodal cubic. And these are the possible Calabi-Yau pair structures that we can put in our ambient variety picture. And here, for example, you can note that we don't have the case where this cubic is cuspidal, because in this case, the pair P2 with this cuspidal curve is no longer canonical. So if you take a log resolution of this pair, we can produce an exceptional divisor such that the discrepancy is smaller than -1. So now, if you assume that we are working with this category of log Calabi-Yau pairs, now I will give you the definition of the morphisms in this category. So, if I have F, a birational map between Calabi-Yau pairs, F birational, pairs. So I will say that F is volume preserving with the pullback of the volume form associated to the target is a non-zero multiple scalar of the volume form associated to the source. So here, this condition says to us that I'm preserving the volume form up to non-zero scale. And what's interesting is that for my own research, when I check this condition, I always deduce that this lambda is always 1 or -1. I don't know what this is saying. And just a remark, it's easy to see from this definition that if I consider the set of self-volume preserving maps of a given Calabi-Yau pair, this will form a group, and in particular will be a subgroup of the group of birational automorphisms of the ambient variety. So group here is the group of self-volume preserving maps. From the definition of Calabi-Yau pair, so if I start with XB Calabi-Yau pair, from definition, this implies that the canonical class plus the divisor is equivalent to 0. So in particular, this implies that the uncanonical class is effective. So from this condition, we can deduce that the canonical class of our ambient variety is not still defective. And by a theorem by Buxton, Demailly, Paul, and Teternel, this implies that the ambient variety is uniruled. So this is the BDPP theorem, Buxton, Demailly, Paul, and Teternel. And this implies that the Kodaira dimension, and the unirule implies that the Kodaira dimension of my ambient variety is minus infinity. And by the minimal model program, I know that if I run it in this variety, I will end up with a more fibrous space. And we can show that for this output of the NP, I can put a Calabi-Yau pair structure. And what's interesting is that as long as we have a Sarkisov program in this context, we have a volume preserving version of this theorem in this context. In the following way. So have the volume preserving Sarkisov program, which was proved by Corti and Kalogirus in 2016. And basically, the philosophy of this result is essentially the same. In the case that here, I will take advantage this diagram. So here I will replace more fiber space by more fiber Calabi-Yau pair. And here I will replace a birational map by a volume preserving map. And in this case, this result says to us that we can factorize this map into finitely many volume preserving Sarkisov links. And all these volume preserving Sarkisov links will be with respect to Calabi-Yau pairs. So here is one, and so all these links will be volume preserving. And it's important to note that the ordinary Sarkisov program, the ordinary one, is a result which is algorithm in dimension 2 and 3, and it's existential in nature for higher dimension. The proof of the ordinary Sarkisov program, the ordinary Sarkisov program does not suggest any algorithm, but we use the term program anyway. And this result here of the volume preserving Sarkisov program, it's a result existential at first in all dimensions. And it turns out that the logic Calabi-Yau geometry can be really useful to study decomposition groups. So now let X be a projective variety, and Y be an irreducible subvariety. Subvariety. The decomposition group of Y in beer of X is given by the group of birational maps of the ambient space such that the restriction to Y will be a birational map. So this is simply saying that these are the subgroup of the group of rational automorphisms of X of the maps which will stabilize this variety. And when X is Pn, we denote this group by deck of that. Just annotation. And what is interesting is that we have this beautiful coincidence. When I consider, we know that if I have, in this scenario, if I assume that my subvariety Y is a prime divisor, and the canonical and the corresponding pair X and Y is a canonical Calabi-Yau pair, we have that this group coincides with the group of self-volume preserving maps of this Calabi-Yau pair. So we can use tools from the logical Calabi-Yau geometry to study decomposition groups, especially in the case of our underlying of our ambient variety is Pn, and this is a consequence of it's a consequence of a proposition. I don't remember the number of this proposition, but it's a proposition from Araujo, Corti and Massarenti, Now I will tell you some results that I could obtain in my PhD thesis and a two-dimensional context and in a three-dimensional context too, by employing these tools from logical Calabi-Yau geometry. Just two-dimensional case. So if you consider C a non-singular cubic, we readily have that P2 with this curve is a canonical Calabi-Yau pair. And now, if I consider, and generally speaking, the pair of P2 with a non-singular curve, this case is the most interesting one in terms of the decomposition group. This is a consequence of the following theorem by Pan, proved in 2007. So if you consider C irreducible, non-singular, non-rational curve, and suppose that exists a map belonging to the decomposition group of this curve, which is not a linear automorphism of P2, which is given by PGR3C. So the degree of this curve is necessarily 3, and the proper base locus of this map is contained at the curve. So this says to us that, okay, the richest, in this case, for example, when this curve does not have a degree higher than 3, so this tells to us that the decomposition group of this curve consists of the automorphisms of P2, which will preserve. And so in the case which is most interesting, is exactly the case where this degree is 3, and it is exactly the case where the pair is Calabi-Yau. And so we can apply all this theory from log Calabi-Yau geometry to study this. And what's interesting is that, assuming that we have, and in this case we have this beautiful coincidence that the decomposition group coincides with the group of self-volume preserving maps. And by using that, in this case, we have a volume preserving Sarkisov factorization. We can show something stronger than this. So if you have this result by myself. So in this case, if I consider C a non-singular cubic, and we pick phi a map belonging to the decomposition group, which is not a linear automorphism. So the full base locus is contained in the curve. This notation also includes the infinitely linear base points for a rational map here. And so this implies that when I resolve the indeterminacy of this point, of this map, all the infinitely linear base points will be contained in the strict transforms of the curve. So this is stronger in some sense when we compare with the Fan result. And by using this lemma, we can show the following theorem, and under the same assumptions. We can consider again a non-singular cubic. As I told you before, the Sarkisov program is algorithm. The ordinary one is algorithmic in dimension 2 and 3, and existential in the remaining dimensions. And the volume preserving Sarkisov program is existential in all dimensions. But since we have this coincidence here, if you run the ordinary Sarkisov program if you run the ordinary Sarkisov program in an element of the decomposition group, the resultant factorization will automatically be volume preserving. So in this case, we have a volume preserving Sarkisov algorithm. And it was really important for this result to have this lemma here. And basically, the idea of the proof is is on the induction of the number of volume preserving of Sarkisov links necessary to a factorization of this map. So just is taken this theorem, the ordinary Sarkisov program is automatically volume preserving for an element of the decomposition group of this cubic. And this result, just to warn you, this result does not hold, both this result and this result here does not hold in higher dimensions because I could find a counterexample. So the counterexample is given exactly by P3 with a quartic surface having a single A1 singularity. In this case, there is an evolution of P3 which will preserve this quartic, but in a such a way that not even the proper base locus of this map is contained in the quartic. So in particular, using this fact, we can obtain a Sarkisov factorization algorithmically, which we can show that cannot never be volume preserving. And now I will tell something about my result in a some of my results in a three-dimensional case.
Sorry, can I just ask a quick question?
Yes, sure.
So about the counterexamples in higher dimensions, so just is this just something like that's like typical, or is it just like an example exists, or like do you usually expect things to? How often do you expect things to fail? Maybe that's really the question.
Okay, yes. Actually, okay, when I was trying to prove this in higher dimension, I just I found this example. But what we know that at least there exists a Sarkisov factorization that must be volume preserving. So we run the algorithm, and at least one of them is volume preserving.
Something's okay.
Yes, but the point is that when you are running the Sarkisov program in dimension 2, 3, you can make certain choices that can lead you to a volume preserving factorization and to actual volume preserving one. So it will depend on how you will run the Sarkisov program. And basically, the key point is that all the centers of the blowups or divisor extractions must be contained in the boundary divisor. So this was crucial to show this result.
All right, thanks.
Oh, welcome. Just now in a three-dimensional case. Now for the three-dimensional case, I consider D a canonical quartic surface. So in this case, this condition implies that the quartic is nonsingular or has ADE singularities. And we can show that this pair here, P3D, is a canonical Calabi-Yau. Okay. And just to show that how powerful these tools are, for example, Araujo, Corti and Massarenti were able to give nice descriptions for the decomposition group of a general quartic surface of P3, for a quartic surface having a single A1 singularity just by only by employing tools from the logical Calabi-Yau geometry. And now assume that we are interested in assume that we have a birational map from P3. Here I am putting the structure of more further space. Maybe I will. From P3 to another more fiber space. Since P3 is a fundamental variety of P rank 1, we can show that the first Sarkisov link in any factorization of this map must be initiated by a divisorial contraction to either a curve or a point. So see curve, P point. And in the case where here I will denote this divisorial extraction by pi. And in this case where the center of this divisorial extraction is a point, in the case, this means that P of E is equal to P. So there exists a theorem by Kawakita exists an analytic neighborhood of P such that pi is the 1AB weighted blowup. And these 1AB are such that AB are coprime. And so this says to us that locally, this divisorial extraction is a weighted blowup. And so if we assume that this divisorial extraction is actually the whole weighted blowup, so because this only holds in an analytic neighborhood of the point. So if we assume that this holds globally, there exists a theorem by Guerreiro that he classified all the weights in this case, which will initiate Sarkisov links. So in this context, there exists this theorem by Guerreiro. And in this case, these weights, if you assume that pi, in this case, sorry, we can assume that the pi is the global weighted blowup. So in this case, the order red pair AB belongs to this list: 1, 1, 1, 2, 2, 3, and 2, 5. And in this result, he gave the whole description of the Sarkisov link. And why is this result important? Because of course we want to study birational maps from P3. We can we study the composition groups, And this result is important because at least we know how to start a factorization in this case. And of course, we know that birational geometry and for threefold, even for trifolds, is harder than it is for surfaces and curves. So here the whole Sarkisov program dimension 3, we don't have actually a real explicit classification of the Sarkisov links. And so what I did was to prove a volume-preserving version of this theorem by Guerreiro, in the sense that I am considering exactly a canonical quartic surface. And so in this case, I need to assume that this map, instead of birational, is volume preserving. And we can check that by using tools from the logic Calabi-Yau geometry. If you have that pi equal, in this case, also assuming that this divisor extraction to a point is the whole weighted blow up. So in this case, we can prove that this point here belongs to the singular locus of the quartic surface. And so this is really interesting because if we start with a quartic surface which is non-singular, this says to us that, okay, the first link must be a divisor extraction to a curve in this case. And in particular, the centers of these divisor extractions are extremely related to the base locus of the birational map here. So in this case, this result says to us that the base locus of any birational, of any volume-preserving map starting with P3 and then non-singular quartic surface does not admit isolated points. So it must be a curve, which can be reducible. And so now my problem was to, okay, since this case, this implies that P is a singularity of D, my problem was, depending on the singularities of P, of the type, determine which weights will be volume preserving. So for this, I will share you my slides, just a slide containing this table. Just a moment. Okay, can you see my slides?
Yes, we can.
Okay. Okay, this is just the statement of this theorem, the form is stated. So in this case, we can show that this pair, there exists a discrete volume preserving variant, which is called coregularity. So in this case, the Calabi-Yau pair P3 with a canonical surface is a Calabi-Yau pair of coregularity 2. And in this case, if I have pi, a volume preserving toric, 1AB weighted blowup of a torus invariant point, and so this point is necessarily a singularity of the boundary divisor. And so up to permutation, so the only possibilities for the weights, which we initiate in this case, a volume preserving Sarkisov link, are described in this table. So here we can see that we have all the possibilities of canonical singularities, and you can see that I have some weights in black and I have some weights in colors. And what happens with these weights in colors? These weights in colors, they will not work for a generic member of the coarse moduli space of quartics having such a type of singularity. So they will only work for special quartics in the corresponding coarse moduli space. Because when the strategy to prove this result is, okay, we will write the general equation of this quartic, assuming some coordinate, assuming some coordinates, and basically we will compare conditions to conditions in order to the quartic to have such a type singularity, and also this weighted blowup, in order to be volume preserving, this will imply some conditions on the coefficients of the quartic too. So basically, to prove this result is basically to compare both conditions at the same time. And when these weights 1, 1, 1 and 1, 1, 2, they will work for a generic number. So if you pick any quartic surface having an A1 singularity, so for example, the only volume preserving weight is 1 on 1, and for the remaining cases accordingly. And basically, this, for example, will say to us at least how to start a volume preserving Sarkisov factorization. And just to let you know, the case where the singularity is of type A1 and A2, these cases were already studied by Araujo, Corti and Massarenti in the paper Rational Geometry of Calabi-Yau pairs. So basically, this result extends the result of Araujo, Corti and Massarenti, and it's also a volume preserving version of the theorem by Guerreiro. And so I expect with this to study the composition groups of quartics having single singularities of these types, and study the rational geometry of the corresponding Calabi-Yau pair. So thank you very much.